And Pedro will talk about the experience of using functional programming, or doing functional programming at Standard Chartered, presumably.
Thank you, Michael. Hi, everyone. I'm Pedro. I'm Managing Director, Global Head of the Core Strats team at Standard Chartered Bank. What I'm talking about today is joint work with colleagues Atze, Dijkstra, and Pierre, Néron. But really, we are reporting on the work of dozens of people over the years. It's a real honor to have the last session of ICFP. I guess that's nearly as good as having the first session. But I think it's a nice way to end, because it should be a lightweight talk, happy story, no typing rules, almost no code. Now, I can only do so much to, in 15 minutes, describe a system that's been around for 15 years. So my goal here is to get you to read the paper, where I talk about this in more detail. So in the talk, I'm going to provide some context, tell a bit about the Mu compiler and language and the wider ecosystem of Cortex, and share some conclusions we found from the use of functional programming at Standard Chartered. So, functional programming in finance, if you look for it online, you'll easily find references going back for at least 15 years at places like Barclays, Jane Street, of course, and Standard Chartered. But let's not forget the spreadsheet. Spreadsheets as functional programs have really been used in finance for far longer than 15 years. Now, whether you consider spreadsheets to be functional programs or not, they were at the core of the use of functional programming at Standard Chartered either way. Back in 2008, there was a bunch of C++ code written by quants to do financial modeling, so things like pricing, deals, and computing sensitivities to interest rates. And our users, trading and salespeople, wanted to make use of that, but, well, they can't just call C++ functions. The kind of tools they use are Microsoft Excel. So we built Lambda to bridge that gap and to make the C++ code easy to use in an Excel environment. So that was implemented via an add-in. But it was already quite functional, so it had a pure interface and supported things like higher-order functions and parametric polymorphism. But then it kind of became a victim of its own success. It started being used outside Excel via some sort of scripting interface, but it didn't even have a module system. So clearly, these scripts were running out of hand in terms of size and copy-paste all around. So it became clear that we just needed a proper solution, a full-fledged programming language. Haskell was a strong candidate for that, but we did not want to lose the things we already had and our users got used to, namely the C++ and Excel interoperability, and also the ability to serialize all values, which is something Lambda already had. Therefore, Mu was created as a dialect of Haskell that would continue to support the things we already had in place. So I told you about Mu, the programming language, but Mu is a part of the Cortex ecosystem that's developed by the modeling and analytics group, of which my team, the Core Strats team, or the developers, is a part of. It consists of many things. Some of it is the libraries for quantitative financial modeling, like the C++ code I just spoke about. The Mu language and the Mu compiler are part of it, but also its interfaces so that it can be used outside our environment, namely Excel, C++, .NET, Java, and most recently also Python. It also consists of several end-user graphical applications. Here you see an example of one. This is actually kind of a launcher for all the other applications. So if you click on each of these icons, you open another graphical application. This is all written in Mu, all of them. It also contains things that do not have a graphical side to it, so server-side components like an intraday risk service or end-of-day pricing batches. It's built, tested, and released automatically on a daily basis, so we have our own DevOps. Now, what are the key differences between Mu and Haskell? I'll list a few of those here. The paper goes into a bit more detail. Mu is a whole program compiler. With that comes some advantages in terms of optimizations that we can do, but it also comes the downside of longer compilation times. It is compiled to bytecode with a runtime interpreter. And this gives us the ability to, say, compile code on one machine and run it on a different machine using a different Cortex version and potentially even in a different architecture. The bytecode and the interpreter do not change often, so code is typically compatible across versions. Mu is strict, but sometimes the semantics can be lazy. Now, this is a bit hard to explain, but essentially, we are pragmatic here. In some cases, it would just feel too different for a Haskell programmer if you were to stay completely strict. An example here is from maybe. So if you call from maybe on a just value, even if your handler for the nothing is undefined, people kind of expect that not to fail. But in a truly strict setting, this would fail. The same goes for error catching. It would be awkward, let's say, if you didn't have some sort of delayed evaluation there. So we annotate some functions to behave lazily as the programmer would expect. Strings are not a list of characters in Mu. In fact, we don't even have a character type. They are implemented natively in C++. Because we want to have this easy interoperability between C++ and Mu, we have a way to call C++ functions natively from Mu. And that's essentially, there's a C++ iFunction interface, and both C++ and Mu functions adhere to that interface. Now, because you can call so easily from Mu into C++ and vice versa, if you start doing recursion, you can easily find yourself in a situation where Mu calls C++, which calls Mu, which calls C++, etc. And tail call optimization becomes hard. We don't have tail call optimization, so we discourage recursion, and it's disabled by default. Turns out, first, we rarely need it. It's only used in under 4% of our modules. I mean, you can enable it via Pragma. But also, like a positive side effect is that it forces people to use recursive combinators, things like fold, which we optimize natively. GHC supports many extensions. Mu supports not as many extensions, so in particular, no existentials in Mu, which also means no GAVTs, although we do have type equalities. Also no rank 2 or higher polymorphism, but we have many of the more standard extensions, things like multi-parameter type classes, for example. Serialization is supported by default for pretty much everything in Mu, and this combined with the runtime interpreter means it's very easy to write code on your Windows machine and then just send it over the network to thousands of cloud nodes and have it run there and then return your results. Our go-to data type for collections of data is not lists. Instead, we tend to use relations. A couple of years back at the Haskell Symposium, I think there was a paper on our one of our typed APIs to the relational algebra library we use. We have a very efficient implementation in C++, and we find that it's a nice level of abstraction together with your usual algebraic operations on relations to operate with large collections of data. Finally, we introduce a distinction between I/O and safe I/O. And again, here, this is just something where we're pragmatic. If an operation only reads, like a read file, that lives in the safe I/O monad, whereas an operation like write file lives in the I/O monad. You can always go from safe I/O into I/O, but not the other way around. And we provide an easier escape mechanism, or perform function, for the safe I/O monad. Conversely, unsafe perform I/O is actually not exported. You can't use it. You have to edit the compiler to whitelist the module to use unsafe perform I/O. Despite all these differences, we are actually looking to make more use of GHC. This is our current compilation pipeline. We start with a Mu source. The front end produces our core-like representation, which we call exp, and then the back end produces bytecode. But we want to actually use GHC to produce GHC core from our existing Mu modules, and then a new component called GHC Mu converts GHC's core into our exp, and then we continue with optimizations in exp-land and with our compiler to the backend, so we continue to have all the advantages of our backend. This should make it easier. Well, it should simplify our code because we can drop things like parsing and type checking, but it should also allow us to more easily be able to adapt GHC extensions. Now for some conclusions. Here are some figures. You can find some more in the paper. So there's over 100 FTE, full-time equivalents, in the modeling and analytics group, and about a third of that is core strats. We have over 7 million lines of code, of Mu code, 500,000 lines of Haskell. The Mu compiler itself is written in Haskell, and under 2 million lines of C++. Talking about lines of code, if you want to see that plotted, here we see from the inception of the project in 2008, the blue line is Mu, that ends up here at around 7 million. You see that around 2014, Mu overtook C++, and the rate of growth of Mu code is clearly higher than that of C++. So we're getting more functional by the day. On the advantages of using functional programming, we have fewer bugs. This shouldn't be something that surprises this audience. Entire classes of bugs disappear because of a strong static type system and memory management. We spend way too much time debugging C++ segmentation faults, and that's not something we have in Mu. Purity by default, control of effects, and almost no explicit array indexation really solve a large class of problems that you may otherwise have to deal with. We rely heavily on data types as structure, so they are used to structure our code. They give us a form of documentation for free, and in fact, a contract. Each financial product, each different kind of financial product, like a foreign exchange forward or an interest rate swap, is modeled by a different data type in Mu. Now, in terms of productivity, and while stressing that this has not been compared in a controlled setting, it is my experience that we typically can deliver similar solutions either faster or with fewer people than another internal team that uses Java as their technology of choice. Now, here's where I would talk about disadvantages, but I do not actually see disadvantages of the use of functional programming in our setting, so instead I'll go over some common myths associated with FP. Interoperability, well, in any large setting where you'll have different components using different technology, and they will have to be able to interoperate. And you can use standard techniques like communicating by database, by file, or by API. So not any particular difference or challenge for FP there. In terms of performance, well, it is a fact that the use of high-level languages can incur some runtime performance penalty, but I think that's often overstated. In our setting at least, we know what parts are important to be fast, like Monte Carlo simulation, and that is implemented in C++. And then for everything else, often you will start with a database connection to the other side of the world that takes 5 or 10 seconds to get back. So then it doesn't really matter if you pay an extra 10 milliseconds for using Mu rather than C++ or so. Hiring is also not a problem. We've hired over 100 people over the years, and it's never been a limiting factor in the team growth or the ability to deliver value to the business. In fact, I think that in a way, focusing on people with functional programming mindset and experience simplifies the problem of finding good candidates. Concluding, I'll leave a final thought, but you can read the slides, so I guess I'll say something else instead. I think we as a community know that functional programming and related techniques can be used to great effect to write better software and prevent common problems that you can run into if you're using, let's say, less structured programming languages. But I think we're often not vocal enough about it, and I would encourage, in particular, my colleagues from industry to come out and share their success stories of using FP in their settings, so that hopefully we can continue to dispel myths and broaden the adoption of FP in the industry. Thank you.
questions?
Kimi Yo, independent researcher. Could you elaborate a little bit more about the management of effects and the control of effects in the Mu code base? Do you use monad transformers? And if so, what are they like?
Yeah, so in terms of effects, I think we don't really do anything particularly different from what is done in Haskell. Different parts of the code base or different developers will use possibly a different technique according to their preference, but monad transformers are still common, for example.
Is Mu finance specific? I mean, your description doesn't show any specifics in finance, but why aren't we using it for anything else?
I can get the last part of your question.
Why don't we see Mu using in other things except finance?
It is not specific to finance. You don't see it everywhere. You don't see it anywhere else because it's proprietary. So it's been built around a lot of financial analytics core, but nothing in Mu really, I would say, is finance specific, other than the fact that it's used for finance.
So are there any plans kind of open sourcing it or something like this?
So open sourcing the Mu compiler would, it's never been built with that thought in mind, and it would be, from a company perspective, it would be very important to separate the important business IP, which is all the financial modeling, from the PL side of things, the compiler. And because it was never built with that in mind, some of this code is a bit intertwined, and it would be pretty hard to decouple those things. So it would be a very significant effort that we have not had the chance to embark on.
Okay, hi, I'm Matthias from Dipella. So can you give us an idea of how they program in Mu? Are they doing like exploratory things to try and figure out what you would like to do, or is it very much we need this connection now and you implement that? So what kind of programming is happening in this language?
So actually these days it really goes entirely across the board. It goes from things that are exploratory and done in a very iterative nature, and to the point of emailing code to users with serialized Mu bytecode that can just click and run and try, and then you email a couple of hours later with a fix. To systems that run in production under a fully controlled setting, with A/B redundancy, and to which we have no access because only a production support team has. So really, all across the board, it's a general purpose programming language. It can do everything, and we do everything with it.
All right, thank you.